In this video, I'm going to build a pulsar synthesis patch using Max MSP. Pulsar synthesis is a granular synthesis technique developed by Curtis Rhodes, who is one of the pioneers of granular synthesizers in general. To implement this, we are going to be looking at waves, wave shaping, phasor ramps, and all different ways to manipulate audio signals. Let's get started. Okay, to start with, I have my sound output system here. Good old EasyDAC Limi tilde with the argument 2. This is going to act as a peak limiter, and live.gain to control the gain of the audio signals that we are hopefully going to be hearing in a few minutes. But first, I do want to think about pulsar synthesis. What is it exactly? How does it work? What do we need to know in order to apply this in Max MSP effectively? Now, the concept of pulsar synthesis was developed by Curtis Rhodes, who is one of the pioneers of granular synthesis, in 1991. And there are not a lot of resources on the subject. There is the book by Curtis Rhodes, Microsound. There is his article, Sound Composition with Pulsars. There is a website by Nathan Hu in 2022 about creating pulsar synthesis using Super Collider. And there does exist a VST, I think this was made in Max, by Recluse Audio. Okay, so I'm going to be using this article, Sound Composition with Pulsars, as the basis for implementing my own understanding of pulsar synthesis. And pulsar synthesis is a subcategory of granular synthesis. It works through generating these waveforms, these particles of sound at regular intervals with silence. And to make this really simple, this little graph here, this little figure here, is all that we actually need. This is the anatomy of a pulsar. This is how the pulsar is going to function. And in our synthesis, a pulsar is going to consist of a brief burst of energy called a pulsaret W of a duration D. That's this little squiggly line here. That's our pulsaret. And this is always going to be followed by a silent interval here called S. So wave, pulsaret, silence, pulsaret, silence, pulsaret, silence. Now the waveform of the pulsaret, here it's a band-limited pulse, but it's arbitrary. It can be anything. There are some examples to the right. It can be a sine wave, it can be a square wave, it can be a rectangular wave. It can be any kind of synthesis building block you might be using. It can be an entire buffer. Doesn't matter. The point is, for pulsar synthesis, there has to be something here and it's supposed to be followed by silence. And the total duration of P, the entire pulsar wave, is then D plus S. And here is the catch. Here is what we have to watch out for. D and S should always add to the same amount. They should always add up to the same amount, which is going to be the frequency of our pulsar wave. They should always equal to the same pulsar wave length. Meaning, if I increase the size of my pulsaret in this pulsar wave, well, then there's going to be less silence. However, if I shorten or condense this pulsaret wave, this D here, then I'm going to have more silence in my pulsar wave. And this modulation is at the heart of pulsar synthesis. And of course, the name pulsar comes from those pulsar stars. I think they do this when they're about to die. They start sending out these brief flashes of light at these very specific intervals, and I think that was the basis for this specific kind of synthesis. Still, we can consider this to be a subcategory of granular synthesis. Okay, going back to Max. Now, how are we going to implement this? I'm going to show you the single object, the one concept we have to wrestle with to achieve pulsar synthesis. And that object is phasor. This object that generates good old wave sawtooth signals, or these unipolar ramps, which we can visualize by using live.scope. If I give phasor a float number or an integer number as frequency, okay, my phasor has frequency of 1, so it is going to give me these ramps 1 per second. And this concept, the fact that this ramp is a bunch of values, a signal that goes from 0 to 1 repeatedly, is at the heart of the matter. If you understand that this ramp always goes from 0 to 1, and it is this ramp that we have to manipulate to achieve our pulsar wave, then you got it. That is all you need to understand to be able to manipulate pulsar synthesis effectively. Okay, But of course, saying this is not enough, right? We do have the question of how do I take this? How do I get this phasor ramp? And I make it so that only a section of this phasor ramp is actually the phasor ramp and the rest is silence. Because that is what I want right now, right? I want to have my good old equation P equals D plus, what was it? D plus S? Let's imagine it's D plus S. Pulsar wave equals pulsaret plus silence. And I want to be able to define the ratio between the pulsaret and silence with a floating point number box, where 0 means that it's completely silent and 1 means that the entirety of the pulse wave is the pulsaret and there is no silence. And for my purposes, I want to represent this pulsaret as a phasor ramp. I want part of this ramp to be a phasor ramp and I want the rest to be silence. To achieve this, I need to again manipulate this range of values that go from 0 to 1, or I need to make sure that I reach the point of 1 earlier than at the end of my phasor ramp. For instance, if I use the multiplication object, multiplication tilde, because we are multiplying a signal, and let's give it the default argument of 1, well, nothing is going to happen, right? I'm multiplying the signal by 1, meaning I'm not getting anything. However, if I multiply the signal by 2, well, look at this now. This phasor ramp is going from 0 to 2, meaning that in the middle of this phasor ramp is the value 1. I have reached the value of 1 in the middle of my phasor ramp. Now, if I manage to cut out the rest of this phasor ramp, if I find a way to ignore anything that comes after that point of 1, I will have silence after this phasor ramp reaches the point of 1. And that can be, in principle, my pulsar wave. Okay, so how am I going to do this? Well, let's start by checking if our signal is indeed part of our pulsarets. As in, is my signal 1 or less than 1? I can use a comparison operator for this. I can use a smaller than, equals, tilde, and then as an argument I can give 1. So is the incoming signal less than 1, or does the incoming signal equal 1, or is this question going to be answered but no? There it is. And you can see that I'm either getting 1 or I'm getting 0. The middle of this live scope is 0, the top of it is 1. And 1 means yes, it is indeed, the current value is 1 or less than 1. And 0 means no, the current value is not 1 or smaller than 1, so it's a value larger than 1. And I can use this information to slice out the rest of this phasor ramp. I can use multiplication, multiply tilde just like before, and I can multiply this audio signal with the result of this comparison operation. There we go. So now the signal is multiplied by 1 if it is 1 or less than 1, and it's multiplied by 0 if it's higher than 1, meaning that it's nothing. It's silent. So what we have here is a pulsar wave where the ratio between the pulsaret and the silence is exactly 50%. And I do want to peer this. Actually, yeah, let's try it. Let's just plug this into our system and let's see how this sounds. Okay, so we are just getting these rhythmical impulses, and if I increase the frequency of my main phasor, okay, it's not so much different than a phasor ramp or a sawtooth wave at this point, is it? Or maybe it is, but we don't really have a method of comparison right now. One interesting thing to note is the fact that if I lower the frequency below 20 Hertz, I'm still hearing something. I'm still hearing these impulses, and that's one of the interesting points of pulsar synthesis to me, as in I can take this synthesis and I can create rhythm and I can transform it into timbre as I increase the frequency of the pulsar wave. But okay, this all sounds good, but now what I want to do in order to actually achieve pulsar synthesis is to incorporate this variable right here. I want to be able to set the ratio between the pulsaret wave and the silence in a way that represents the ratio between those two values. And first of all, I want to start working with signals, right? So I'm going to take this ratio value Again, 1 would mean the entirety of the wave is the pulsaret, and 0 would mean entirety of the wave is silence. And I'm going to convert this into a signal by using sig tilde. Now when sig tilde receives a value, it's just going to report that value continuously as a signal. And to receive the right value to multiply this phasor ramp with, I need to divide 1 by this incoming value. Right? So I need to create, again, one of those strange looking objects if you don't know what's exactly happening. Exclamation mark, division, tilde, and then the argument 1. And this is going to make it so that the incoming value is used to divide against 1. 1 is divided by this incoming value. We can use a number tilde object to see what comes out. So 1 would be 1, 0 would be 0. However, if I go from 1 to 0, you would get all these cool, wacky values with which we need to multiply our main phasor ramp. So if I plug this here, I should receive, there we go. Now this wave, now my pulsaret is only 15% of the entire pulsar wave. And if I type in 0.5, well, now it's 50%. If I type in 1, well, now it's the entire thing. If I type in 12, things get a bit wacky. That's maybe for a future video. So let's just stay within 0 and 1 for now. All right, and as I'm changing these values, you might have noticed that there is a little bug here, as in there's a little visual glitch that's going to be an auditory glitch as I change these values, and that is the fact that this phasor ramp distorts as I'm changing these values. And maybe we might be able to hear this if we plug our system back in. Okay, right now it's rhythm. I'm going to turn this up. That was a sawtooth wave, and now I'm going to manipulate the ratio. Alright, I kind of clipped it there for a second. Hopefully your ears are well protected. That's why we have this limmy right here exactly for that purpose. But the point is, there is a small amount of aural glitch involved here because of the fact that changing things midway in the middle of our phasor ramp, no matter what the frequency is going to cause glitches. It's going to distort the waveform in a way that we don't want. So we have to come up with certain systems to make sure that changes are applied only at the beginning of our phasor ramps. And to achieve this, we are going to do two things. First of all, I'm going to give an extra attribute to my phasor, a phasor tilde object, and that is sync update. Sync update should be set to 1, and when sync update is set to 1, the phasor frequency is only set at the end of its cycle when the phase jumps to 0. In this mode, phasor will not instantly change its slope when it receives a frequency change, but it will instead wait until the phase resets, and this can prevent typical glitches, etc. So I'm going to have this right here to make sure that changing my frequency in the middle of a waveform, in the middle of a phasor ramp, is not going to affect the current phasor ramp. But that is not enough, of course, because we have to take this signal, this value at which we are multiplying the original phasor ramp, and we have to make sure that this passes through, this gets updated at a specific interval, that of my main phasor ramp. And for this, I need to introduce two new objects. The first is what tilde, one of those esoteric names, slightly recently introduced in Max MSP. And secondly, I'm going to be using saw, S-A-H, or short for sample and hold tilde. Now, what is a very versatile object? It's a really useful object. If you look at the help patch, you can see there are a lot of functionalities and things you can do with this object, but I don't care about that right now because I'm going to be using the good old functionality of the object when it comes out of the box. And what is going to do when it has no arguments or attributes is that it is going to trigger or generate these impulses at the beginning of phasor ramps. Right, you can see here I'm getting these tiny impulses in my signal when I plug in my phasor into the inlet of what. And this is going to be important for when we use sample and hold. Sample and hold in this case requires a single argument, and that is the threshold value. I'm going to type in 0.5 because I know that my impulse is 1. There's a bunch of zeros, and for a split second I get an impulse of 1. So I'm going to plug in the signal I want to sample and hold in the first inlet, and I'm going to plug the control signal, which is what is sending out, into the second inlet of sample and hold. And how sample and hold is going to work is as such. When sample and hold receives a signal into its first inlet, it is going to wait for the trigger input or the control input to receive a value that goes that starts from below this threshold and goes above this threshold, right? So each time this signal goes from below 0.5 to higher than 0.5, it is going to sample whatever is coming in and is going to constantly send out that sampled value. Meaning that in a system like this, no matter how often or how fast I change this, it's only going to get reported through sample and hold at the rate of what, which is the rate of my main phasor. And we can try this. If I again set this to 1, and I change its ratios, you can see that, whoops. All right, let's address this problem. So if I dip below 0, we do actually expect some glitches and some impulses that shouldn't be there. So I'm going to use clip tilde to limit the incoming signal values between 0 and 1. And this should ideally resolve this problem. Okay, now if we are back and if I type in 0.5, there we go. Now it's half of the signal and I can manipulate this value. And my phasor ramp, well, it's not being distorted. It's always that perfect triangle. Pythagoras would be proud of his triangle, and so am I. Look, it's beautiful. All right, so this means now we can actually hear pulsar synthesis. We can actually hear what it sounds like. And look at what is happening. It's like we are filter sweeping through the signal, even though there is no filter, DSP or otherwise, in this patch. So what is happening is that as the ratio between the pulsaret and the silence changes, there are different formants that are peak formants that are formed in the sound, meaning that there are certain frequencies emphasized in the resulting signal, leading into this nice filter sweep-like effect. Now, another thing we can do is to actually explore this pulsar synthesizer, right? Because this is not all of it. This is not the basics of pulsar synthesis. And the main point of pulsar synthesis is the fact that we can change the pulsaret waveform. So why don't I try something like a sine wave? Why don't I try to use a sine wave instead of this unipolar ramp I'm using in my current setup? And I'm going to be using a special way to work with sine waves. Now, as you might know, cycle tilde is going to generate sine waves, right? If I use live.scope, and if I give this a certain frequency, there. This is a frequency of 1, so I'm getting 1 sine wave per second. However, if we are controlling the sine wave through some other matter, we can also use the second inlet of cycle. And this is going to set the phase of the sine wave, as in which point of the sine wave am I working with. And if I have this continuous ramp that goes from 0 to 1, through a certain frequency, and I use that to determine the phase of my sine wave, I am going to get the sine wave exactly during that ramp. So phasor with a frequency of 1 is going to give me the exact same thing. The only changes, if at some point in my signal there is a ramp from 0 to 1 and then stays at 0, well, the cycle is going to stop at that moment. So I can really condense my sine wave as a part of my pulsaret wave in my pulsar synthesis setup right here. Meaning, this right here, there we go, and sets this 1 as well. I have my ramp, and I'm going to do the exact same thing, cycle tilde, and I'm going to make sure the second inlet of cycle receives the resulting pulsar wave. And what comes out is going to be the sine wave. And just like before, if I change the ratio between the pulsaret wave and the silence, I should be receiving different distorted sine waves. Of course, we should see how this actually sounds. Now, do notice that we are just hearing a sine wave right now because the pulsaret length, the ratio is at 1, so we're just getting the entirety of the wave. Now, let's introduce some silence into the mix again. And look at how the signal is being distorted. And again, the cool thing is we can go back into the rhythmical range by having silence into the mix and lowering the frequency below 20 Hz. And now we have rhythm. Finally, let's see how we can incorporate some kind of audio buffer into the mix. And I'm going to do this by creating the buffer object. So buffer tilde, I need to give this buffer a name. I'm going to call this ant. And let's use the classic Anton.aif. This should be a built-in sound sample that comes with your Max MSP installation. To see if this is indeed loaded, I can use the waveform tilde object with the attribute buffer name and then the name of the buffer, ant. And there we go, we have our signal here. Now, you might know we can read through these buffers using the wave tilde object, which is essentially a wave table. Right? So if I give the name ant to my wave object, or wave tilde object, and I have a phasor ramp that goes from 0 to 1, for instance. I can use live.scope here. Well, that audio signal is going to be read at exactly that rate. The faster the phasor is, the faster that buffer is read through. Essentially, the buffer itself is treated as some kind of wave shape or waveform. But the important thing is this wave tilde object expects values that go from 0 to 1, which will correspond to the position of my buffer, the position of the playback of the buffer. So instead of using cycle, I can take the resulting ramps of my Pulsar synthesizer and plug this into wave tilde with the argument ant. And plug this back in. And let's see how this sounds. Very granular. Motoric sounds. And I feel that using these large buffers are very effective when we are on the rhythmical level, when the frequency is below 20 Hz. Of course, we can also just target a certain section, right? So we can take this ramp that goes from 0 to 1 and we can, for example, change that range using scale tilde to, let's say, 0.3 to 0.5. So just a certain segment of my buffer. And here we can get these very cool granular textures. And as a final, let's add some randomness into the mix. So let's make sure that the generation of these random values are happening at a random rate. So I'm going to use noise tilde, which is going to generate random noise, so a different sample value between -1 and 1 on each sample. And I'm going to scale this, scale tilde, -1 to 1, and I want to scale this to, let's say, 0.2 to 0.8. And this value, instead of my ratio here, is going to go into clip and into this algorithm. Wonder how this is going to sound. There we go. We can create a bunch of cool textures with this, and if we want, we can use this second to last inlet of scale to change this 0.8 value right here. So what if it's something lower? 0.4. Or what if we remove this clip and we go higher than 1? So there you go. Pulsar synthesis is indeed a powerful tool that you can use to create these robotic sounds, textures, grains, as well as these fat synthesized sounds that emulate filter sweeps as well as other frequency operations on a signal. You should be able to use these and automate these further to create many things. For instance, Curtis Rhodes takes this to the next step by using pulsar synthesizers to control parameters of other pulsar synthesizers, which is definitely something worth checking out. In any case, enjoy experimenting, create cool things, and thank you for watching.